that we're all familiar with in daily life, right? Apples. This happens to be a very ordered arrangement of grains, where the grains are the individual apples. Here, these are grains, but they are cylindrical and they are cakes with Guinness. Here, the grains are actual grains in the silo. M&Ms, peanuts. The grains get bigger, right? People, even bigger. Cars, hugely bigger. This is a protoplanetesimal. So now we're talking something up to about 10 kilometers in outer space. That's how planets form. And then let's flip the switch and go really, really small. What about these guys? These are now nanoparticles. And then we have some more nanoparticles right here. They're not as ordered, and these red ones are 5 nanometer diameter each of them, and these little gold ones, they are about 50 nanometers across. They're all granular materials, the way I define it. So what do I really mean by that? And by the way, just from this list, you see that some of them are stuck and static. They're just sitting there, and nothing happens. They are obviously moving here. They would like to move, but they happen to be stuck in some sort of static jam. Right? Here the grains are stuck enough that somebody can sit on it and read a newspaper. And these, there's some sort of emotion, and hopefully when you open the silo, stuff comes up. So very, very generally, I like to define granular material essentially as some sort of a coarse-grained concept. So you have stuff. And you draw a circle somewhere, and you say whatever is inside here, I call it grain, and then you draw another circle over here, or a sphere or some volume, and whatever is in there constitutes a grain. And the issue then becomes where you draw the boundaries. And typically the way I like to think about that is that there's internal degrees of freedom that I somehow don't want to care about. Right? So a particle in the box for quantum mechanics has only a few degrees of freedom, so there's interesting stuff happening right there. That wouldn't be it. I need to take more particles in there. So for a quantum mechanical nanoparticle, I say about 1,000 particles, which is about 5 nanometers across, 5,000 particles. That's a grain. That's a good one. So you integrate over these degrees of freedom, you average them out, or you ignore them. So what is left are interactions between these grains, and I want to say that for a granular system, you focus on short-range interactions, essentially contacts. So what that means is electronic tunneling is a wonderful interaction. Okay? Look, sorry, we're making a little detour here, but to set the stage, right? I know it's heterodynamics complex. But that's where granular materials got started. So when I was a graduate student in the 80s, granular materials were percolating metal films. If you look at the National Academy of Sciences and you type in, member roster and you type in granular materials, you find people who work on superconductors. That's what that was. Little grains, typically percolating. And the interesting thing with all the granular materials is that even though you might know everything there is about each individual grain, something emerges when you put them into contact. Some new stuff happens. For example, this could be a piece of metal. This is another piece of metal. If you put a battery across that, there's obviously no current flowing through it, so it's not a metal, right? But you push them together and something happens. Or you bring them closer, they're tunneling, and now something new happens. You look at a metal insulator or insulator superconductor transition. That's what granular materials did in the, well, let's say in the 80s, but starting already earlier in the 60s. So it's really materials that have to do with interfaces. And in those days, the individual grains, they were usually stuck on a substrate. But then in the 90s, or maybe in the late 80s, and beginning of 90s, there was another class of materials that rose up and came to our attention. And in those cases, the grains were actually moving. And let's talk about now macroscopic systems, so sand grains. But again, the interaction happens at the interfaces. It's the nonlinear friction. It's the dissipation that happens at contact interactions. Okay? So those were the granular systems that you might think about nowadays. That's the ones I actually want to talk to you about. And again, there is an interesting new emerging behavior that comes from the collection of the grains. Right? So as a collective entity, they can be stuck. Or as a collective entity, they can be flowing. When you think about traffic, you can talk about traffic flowing and traffic being jammed. And it's the same cars. And sometimes you wonder how that can be. It's just a tiny little fluctuation someplace, and suddenly the whole thing behaves more like a solid fluid. And these don't have to be associated with physical boundaries. There are people worrying about crystal lattices right now where superconducting fluctuations take place, and they define and correspond the system, and there are certain tunnels where these fluctuations nucleate, and they might dynamically rearrange. But that's possibly one way to think about it. Also granular system. And then more recently, there's a nice review by we wrote a little of about granular nano structures, right? So that's these things I showed you. Okay. What do all of these things have in common? It is that the interesting physics happens at the mesoscopic scale. And so in contrast to many of my colleagues who say mesoscopic is stuff that happens below 1 micron, I say mesoscopic is like mezzanine, mezzo-soprano, it's in the middle. Right? I mean, that's literally what it is. So it's not a single grain, it's not a continuum description. It is precisely knowing about these interfaces and these interactions. That's where these local forces happen, where there are constraints, where there are certain symmetries, where the packing matters, where the interactions matter. And in particular now, these are short range interactions. Okay? And the interesting thing, of course, will be then to somehow bridge these scales, but I want to focus mostly on this intermediate part. So, this is what I call a granular material. And after having done that, I want to now specialize on this macroscopic variety of stuff that is, for example, in an hourglass. Okay. So we're going, now we're getting away from all the superconductors and all that and go to this. Okay? So, as I told you, there are these interesting transitions. So in contrast to ordinary matter, where you of course can also heat them or cool them or put them under confinement, here the transitions happen under the same pressure, volume, whatever. Look at this sealed hourglass. The stuff is liquid-like right here, but instantly freezes into a solid, right? In fact, there's an angle of repose. The pile is not totally flat. This guy is sitting on this heap right now. Obviously doesn't fall through, but you know if you just tilt this a little bit, a whole bunch of peanuts will flow out, right? And this is a beautiful model system for behavior that is not in equilibrium because these particles are typically, in the way I want to think about them, now large enough that there's no grounding motion, so that ordinary thermal energy is irrelevant, and typically gravitational energy is dominating everything. And then if you think about this dissipation and the friction between particles, so the interfaces now, and the contacts, that is a way to lose energy. So the system that is not constantly fed with energy will come to a rest and will get stuck off in a metastable state. And furthermore, these particles are large enough so that they can get into each other's way, as opposed to point-like molecules. All right, and we'll talk about consequences of that go under the names of jamming and dilation. So let's suppose we go to the simplest system at this time, just spheres. And let's suppose they're all identical spheres. Then one question you can ask is, what happens if I pack those spheres in 3D space, right? Just like these apples we saw, oranges. And the densest pattern we can do is actually not space filling, but there's 26% empty space, even under the most ideal situation, which would be an FCC crystal. Now, if you just threw the particles into a box, even of infinite size, there's no way that they would automatically find this. This is essentially measure zero in configuration space. Because there is an abundance of other possibilities which go under the name of random closed packing or maximally jammed arrangement, and that means that you can only go to about 64% of the volume filled with spheres and 36% of the volume empty. These are mechanically stable, and if you now take more stuff out, eventually you come to the point where under gravity the whole thing will collapse. Right, and that happens about 56%. So now, this is a really interesting that there are interesting consequences. And so this is somebody you might all know. And so, 100 years ago, he says, look, this is a crazy material, this granular material. He didn't call it that way. He said, look, if we take ordinary materials, so elastic solids, normal solids, and we want to make them, let's say, lighter, we shake them up. That's the basic idea. But, and if we want to get a dense solid, we just compress it. Right? But this material, which he calls a corn now, so corn being one example of the granular material, it's just the opposite. So, if you try to press it, rather than getting denser, so in the language that we use now, there will be shearing and dilation, and actually it will expand and grow. So that's pretty crazy, right? From just simple steel. And to understand that, just imagine you all sitting in nice rows here. Suppose we were all a little bit more close packed, and this row right here in the middle would want to move. So you squeeze something so hard that you induce shear eventually. Right? In order for it to move, because of this interlocking here, these guys have to go a little bit to this side, and that allows you to move through. This, by the way, is the reason why you get this halo when you walk by the beach. Right? And everybody knows how that works? So you walk along the beach, there, the water line, and you put your foot on it. Your foot makes an impression. That means you sort of stress. And there was an impression, that meant there was actually strain. Since there was strain, this is a granular material, that means there must have been dilation. Since there was dilation, the volume expanded. That meant the water sank in a little bit. It drained. Since it drained, the index of refraction changed because some water got away from the interface and it turns light. So, a beautiful example. So there's some unique consequences for this granular material, class of materials. If you take the energy out, like with a sand pile, you just dump the spheres into a bucket and then don't do anything further, they're just stuck there, right? There is no grounding motion. And typically that state, as I said, was not a crystalline state, but this random packed state, maybe the random densest packed, but not even that, somewhere between 57 and 64%. So we have to deal with metastable, amorphous situations. It's difficult. I'll talk about that a little bit later here, that the structures that evolve, both the physical structure, but also the structure of forces that maybe are transmitted through such a system, are inherently heterogeneous. So now you've got to deal with heterogeneity. It's inherent, so you can't just get away from that. And the reason I'm telling you all of this, by the way, is to just say that something is silly and simple, innocent looking as a bunch of spheres. Right, already gives you this amazingly rich and vexingly difficult set of behaviors. So what else? Oh, now two grains come together. Okay, so there's macroscopic friction. I think most of us would be hard-pressed to say that there is an ab initio theory for macroscopic friction. Right? I mean, we know how to deal with quantum particles when they come close together, but to deal with macroscopic particles, it's actually rather difficult. So we use effective parameters, friction coefficients. But basically, you know that it's the surfaces, nanometer scale properties of surfaces come in here, even though we're talking about macroscopic properties of particles, right? And then you can have that plus also various particle geometries. Imagine you get away from spheres, and now you get concave particles that interlock. Very complex. Then this dilation is actually almost like a positive feedback. Imagine somewhere in the material, as a response to applied stresses, it is actually expanding and allowing things to flow. Well, once things flow, it might expand more. So this is a positive feedback, so you get already an idea that these things can fail in a very dramatic way, and so that gives rise to things like avalanche. Right, so the dynamic behavior of this stuff is actually rather interesting and quickly can get very complex. Talking about that as an experimentalist and as a theorist, so what can happen? So if I take a steel ball and bounce it on a steel surface, the impact times are of the order of a microsecond. So 10 to the minus 6. On the other hand, if we take a collection of steel balls, put them in a bucket, and I said, of course, that nothing will happen at that point anymore. But if you now cap it or you wait for trucks to drive by and you say, well, so slowly this thing is trying to find a better configuration. So it settles, it ages, right? It's a glassy system. Could easily be 10 to the 6 seconds, maybe it's more, right? So the 12 orders of magnitude in time. That's hard for people who like computers. How do you take care of all of that? And then the length scales, we said, well, you know, nanometer fractional properties, 2, maybe 10 also particle diameters. That's where these heterogeneities live, and we'll see. So these are really interesting issues, and so this is exciting. These are challenges. This is really cool stuff based on a bunch of simple spheres. So, all right, anybody seen this game? You can buy that. I had it as a kid. Who has played with that? All right, good. So you know how that works, right? It's a movable top part of this frame, and this is fixed, right? It's the 2 dimensions. So it's easy to see. There are these little cuts in there. You jiggle it up to some random configuration. You let this slider come down. It locks it into place. And what's the goal of this game? To pull out as many of these pucks as you can before something moves. Let's say the boundary moves. So what you have to do right now is you have to guess which one can I take out such that the overall structure doesn't change, right?
Cool.
What?
That's really cool. I've never seen this.
You can. So look, we are really good at looking at geometry, right? Geometrical relationships, but we're really not good at imagining where the forces go, right? So now we're talking about so where are the forces? All right, here's an easy one. I stated it so many times, you'll agree with me that probably this guy can pull up, right?
Yeah.
All right, so that's easy. Look, at these big ones, you get more points. You also have more neighbors. So this is a low point number, so 5 points, cool. But then it gets hard. Well, maybe, I don't know, maybe this one, maybe another one, but you can imagine there are certain ones, if you pull on those, maybe this guy, there's nothing from here, nothing from there, right? Some others, the whole thing collapses. So I loaded an amorphous configuration in 2 dimensions of particles with some stress from above, right? And the stresses have to come down and be taken up by the boundaries. It's Newton's law, nothing is accelerated. Static, right? But how they go through is a different matter. And if that was molecules or water or something like that, you know that on average, you know, it would be everywhere the same. And you can integrate out over all these molecular degrees of freedom. Here, that's not the case anymore, right? And so let's say I know the force because maybe I calibrated that I put on here, the stresses on this boundary. What are the local stresses if I move along here? For example, is this guy pushing really hard right now? And maybe this guy is, but this guy isn't. So there is possibly at every level, in fact, there is a heterogeneity in the distribution of forces, right? This is just scatters. In fact, you can visualize that really beautifully if you use particles made out of, let's say, plastic, polymetallic encapsulated, PMMA, and put in between crossed polarizers. So polymetal methacrylate does something called pressure-induced birefringence. So it rotates the polarization if it's pressed. And here's a simple experiment where it's pretty much dark, where there are no stresses, and really bright, where locally the stresses rotated the polarization, and then underneath the cross polarizers you see it light up. And a more beautiful example of this, Bob Behringer's group at Duke, and Bob, in fact, in his group, they were not with this resolution, but with higher resolution, they're able to look at essentially the stress field in each grain and really quantitatively figure out what the local contact stresses are, right? But let's go back to this question. What would be the distribution of stresses along here? Here I put in some wedges to disorder this thing a little bit, because in 2 dimensions, equal sized disks, they will very quickly crystallize. So this is just a show and tell. But remember, in 3-dimensional spheres, they will not even get close to a crystallized state. So if you did that now, this experiment, right? What would be the distribution of these arrows? And each arrow is the magnitude of the local force that you measure at the bottom. I would have thought, if you had asked me a few years ago, that if this is the magnitude of the force. So these are vectors of force. Let's just say I just take the magnitude, the normal force. You're hitting this bottom boundary, right? And I measure underneath each grain, and I say, what's the probability of finding a certain force F? And I average over one layer. And there's obviously got to be somewhere a mean force F bar, and then some distribution around it, all right? Because not everything is lit up in the same way. Obviously, there's some brighter spots than others. So find what would that look like.
Did you say average over one layer? Within one
Yeah, I just average over one layer.
one line?
Yeah, well, or in
Because
three
it's all-
dimensions, it would be a layer. Here would be a line. So in this particular example, it would be just going along the bottom, looking under each grain, and writing down what the force is. And usually you'd expect, of course, what do you think? I would have expected a Gaussian distribution, of course, by the statistics. So I would have expected something like that. Now, let me plot that a little bit differently because I'm interested in tails here. So I plot the log of this thing, all right? And then a Gaussian, of course, would look like a parabola, right? All right? So, big surprise, this is what it looks like. So this is log probability versus non-normalized force, the average forces right here. This is a signature of a granular material. It says that you have, on the one hand, a preponderance of very small forces, right? So, and also you can see that lots of dark stuff. And then you have a few unlikely but very strong force chains. Those are these bright ones. And the interesting thing is that this comes down as an exponential, so linear here, and it says that basically, so the cartoon of this would look like this, like that, and the Gaussian will always be underneath eventually, meaning that there is a likelihood, so whatever your confidence interval or your engineer, you want to design something so that the local boundary stress doesn't exceed the thickness of the concrete wall, you set your design criteria here. This granular material has a higher chance to hit that than would the Gaussian distribution. Right? So you always have to worry about these things. And we know that this has to have this shape in hindsight because there are these situations where the force is split. Like this you would call a keystone. You build bridges essentially by having keystones. Arches and bridges, and in churches you can walk inside a church because of keystones. Otherwise the whole thing would just collapse. So these places, they divert forces towards the boundaries, and then here it's essentially force-free. Right? This is the heterogeneity that happens on the order of 10 particles. And you cannot possibly get rid of that in granular materials. Makes it interesting. Makes it difficult. It's a challenge, right? So how do you live with a material that is like that behaves like that always will do that? And if you jumble it up a little bit, then it would rearrange these force paths. So this is a signature of a particular arrangement. And which way things split will depend to quite a significant degree on the nanometer scale of the interfaces right at on top. Right, which you can't control. So, the statistics on the other, even though this is one particular realization, the statistics are always asymptotic to this. So this is now maybe 200,000-300,000 data points average together. Yes?
When you say always, you mean is it the same system, or what do you change?
No, so this is great. How do you get these statistics? Notice something. This is 1, 2, getting towards over 2 decades in probability, right? But the other examples that we have up to 4 orders of magnitude, which is really then pushing the limit of what you can do experimentally. It is currently beyond what you can do on the best computers out there in 3 dimensions. But this is an ensemble average. Okay? And this notion that there are inherent heterogeneities in the system forces us to rethink also what we mean by averages. So for example, you can't just wait in time, and there's no temporal distribution. there's always this question whether or not the system size is large enough to allow for averaging in the system itself. Now, if I just said that the typical heterogeneity length scales up to 10 to 100 particles or so, then if you make that much larger, you'd probably see. But really, you have to redo the experiment many times to build up statistics like this. And just because there are two sets of data points here, the light symbols and then the dark symbols, this is in a system, three-dimensional system, a bucket like this, where we measure both at the bottom, that's actually dark, and also at the top of the system that was squeezed from the rock, right? And they have the same distribution in this ensemble average. So this is a telltale behavior, very much unlike what you would get from the ordinary statistics. Now, this is a static system, and in fact, it is now a confined system, and that is particularly rigid. I mean, you really put load on it, and it's not flowing. But you know that you can make a granular system flow. I tried to buy one of those this morning. For some reason, I don't have that here in Boulder. It's what I can help within my walking range. But all of you from Europe, you know, good vacuum packed coffee is hard, like a brick. You can, you know, kill it with it, but you can hurt somebody. You take it home, and what do you do with it? You snip open a corner, and you pour the stuff out. So now it flows. The very same stuff, same temperature, same everything. And the only thing you did is you allowed it to actually expand a little. So you went this transition between a density, a packing density where it is too close to move, called a jam state, and a density where it can move something. And the interesting thing is, you know, you don't have to do all that much. Maybe you have to wiggle a little bit. But you know that the same thing happens with traffic. It doesn't have to be a traffic accident. Most of the time you hit yourself in the forehead and you say, now how come there was a traffic jam? Because I don't see anything, right? It's tiny density changes that allow this to lock up. Right? It is essentially a geometrical phenomenon. So jamming is just geometrical confinement. Particles get so close to each other that they cannot move past each other. They can't shift. Turns out it's just a few percent. In fact, it often can be less than a few percent. Now, this is for macroscopic particles, and it turns something that is flowable on one end, the density spectrum, to something that is rigid on the other end. Now, there are many other systems, many different length scales that behave in similar ways. For example, molecular systems here too. So, window glass, molecules. It's actually a liquid structurally. It's a liquid structurally in the same sense that this stuff structurally, I mean not in 2 dimensions, but in 3 dimensions, is amorphous. Right? The holy grail in X-ray and matter physics for the last 30 years has been to find a smoking gun signature of the glass transition using X-rays, and you can't find it. Structurally, nothing jumps at you, even though you know the viscosity goes maybe 12 orders of magnitude up at the glass transitions, of a whole range of materials. And here the rigidity really goes from flowing to brick-like. Right? So this has led a colleague of mine, Nagel, and Andrew Liu, who's now at Penn, to come up with a conceptual notion of something that maybe connects this type of behavior that we know in liquids or molecular systems with what I just talked to you about in the more macroscopic granular systems. And so there are 3 axes, just in general. So for the molecular systems, temperature is more relevant. If you cool temperature, you get into a glass. I mean, the window glass will flow if you take a blowtorch to it. So you have to come down here. Now, for the systems with a coffee, temperature is irrelevant, kT, but you change the free volume per particle, so you run along this line. And in principle, you could take this, like I told you, densely packed system of spheres or coffee and just really shear it. Now it would need to dilate, but once it does, it will flow, right? So you could actually get it across this bond, right? Most of the work in this field, because this is a complex situation, has focused on this point right here, point J. And the idea is, and has been, and it seems like it really works, that this is a equivalent of a phase transition. Yet, of course, it's a non-equilibrium system, and you don't think about it as a formal phase transition, but it's some sort of special one. In fact, it may even be a good score. I'm not going to talk to you about that right now. But suffice it to say that most of the work has looked right there, and also looking at along this line, marching around here. Now, a few years ago, maybe 2 years ago, Sid and I were sitting in my office in that case and saying, this is great, we know all this stuff, but can you actually do something with that knowledge? Now, can you do something that doesn't already exist? I mean, explain window glass, smoking, coffee, but can you make something? And so, we tried to use jamming to actually design some stuff. Remember, granular materials might be actually interesting after we talk about all these complications. Low density, right? 64% max, maybe less. Disorder, hey, that could mean self-healing also. So it doesn't matter if something rearranges a little bit, finds another metastable state. And then, possibly you could move and march across this transition really, and you could go from a malleable state to a rigid state, and you could use that for something. So here's the idea. What if you put the material, let's say coffee in a bag? This is a rubber bag hanging down off a robot manipulator, and this is John Amen's hand. He's at Cornell, and we just pull the vacuum right, and you see the thing is pretty rigid. Try it at home. It's easy to do. So now you have to make yourself an instant mold. It's totally conforming to surfaces or to whatever you do with your hand. Right? Okay, how about if we now use that to make a robotic gripper? Right? So the idea is you bring something over an object and then you harden it. I mean, first of all, it conforms to this object, and then you go across the jamming transition, you instantly turn it to a hard mold, and you can use that maybe to get something else. Turns out it works like a charm. So here's a movie of this. Look at this really odd-shaped object. And what you see there is this robot arm that is programmed to go to that particular position. But in contrast to other robots where you have a lot of eye, computer coordination, sensors, whatever, all the tricky part is offloaded on the material. So you have simple, innocent glass particles, or coffee grounds in this case, do all the computations for you. Fragile object, you don't need to reprogram the gripper to pick up the metal piece afterwards, or let's say a glass right there. It even withstands torques, because actually this whole system right now is hard. It went across the jamming transition. And if you get yourself close to the jamming transition, you only need maybe 0.5% in volume change. So it's not really pinching all that much. If you had it over your finger, you wouldn't say, ouch, you would hardly notice. Right now, there's actually 3 mechanisms that all work together. One is interlocking where the stuff flows into crevices and whatever. Another one is just simple friction. And the third one is even suction. So they all work beautifully. And you can, in the end, even pick up stuff. And okay, what you'll see is not writing, but drawing. And now it is all an issue of programming the computer, right? So this is actually really cool in situations where you don't have the luxury of a lot of sensory interaction between your hand that you made robotic hand. You don't need many actuators, no hinges, no motors, no nothing, just a simple bag filled with rings. All right, what else can you do with it? So Pecco and I were in the StarPod program, and so one other thing that we worked on is robots. So here's one of the world's few sand robots, right? So these are all filled with sand, and this works. This is not totally soft. This one is really, really soft robot, so Pecco built one stuff too. Right now, you know, it is tethered still, this vacuum being sucked in and out. This is done together with iRobot. And now they evacuated it, and now it's rigid. This little guy even has a little camera. So it can do all sorts of silly things. I don't know why they did that, but so now the issue is programming it, right? And so what you really do, you take 1 degree of freedom, it's a so-called McKibben actuator. It's the central thing here that you move back and forth, and it's a linear degree of freedom. But you put essentially jammable sandbags on the outside, and depending on where you jam them, they will go down, go up, go to the sides, right? If you put 4 of these things around it. And so in this case, these are the first steps of this silly little robot, and it is all, down to actually programming it. And right now they only got the 4 front legs programmed, and it drags its hind legs. But hey, that's a good one. If you want to read more about this, that's a nice paper actually. Okay, so this is kind of cool. Who would have thought, right? So here's a biased list of what's kind of hot right now for me in Granular. And this is going from static to moving. There's a lot of excitement right now worrying about particle shapes, especially Pep and I were just talking about that, going away from simple spheres. So plot shaping, there's M&Ms and oblate particles, but everything anybody has ever done, anything anybody actually knows about a convex shape. Nobody knows anything about the pattern of concave shapes. Right? There's mathematics, concave shapes. There's mathematics, computer science, physics, all of these fields interested in this, I think. It's really exciting and wide open field, so you guys should really think about it. There's the jamming, unjamming transition away from that concave. I think that's exciting. There's work being done. What about the fluid state? So now you're unjamming. All right, we'll talk about that. But what does it look like? Especially also if you now go away from just having grains and put some other medium in there with it, maybe just the air. And this is something that's quite interesting now. The physics part of the granular field is really worried about particles where you can neglect essentially all these interactions, mostly at least, and where you certainly only think about repulsive interactions, repulsive short-range interactions, contact forces. But there are also attractive contact forces, liquid frictions, van der Waals forces. We'll talk about that. Right? This is quite interesting in emerging now in the direction. So what I do in these lectures, I will look at examples for these things. Any questions? This was a long introductory part, but I thought it was important to give you a flavor for why I think this is exciting and that there are many, many open things to look at. And now we'll get a little bit towards the fluids, okay? Anybody with me? Yes?
What's the name of the paper that we talked about?
The paper?
Yeah, you have it.
Oh, this one. Just it's on my website, so if you look at the website and look at the proceedings of SP. Okay, so this is obviously liquid, right? Fluid. How do you know? How do you know? Why is that water?
It's not flowing.
Because it falls up. And if you jiggled it, there would be waves, right? And there are little droplets that came off. So if you take any liquid, and you ask yourself, why is a liquid a liquid? I mean, how do I even know it's a liquid? There are 3 macroscopic parameters, because we integrate out all the molecular degrees of freedom here, right? We don't care what the molecules. So what are the parameters we care about? We just heard about it. There is the viscosity, there is, of course, the density, and then there is surface tension. And the surface tension obviously leads to this minimization. And then there's gravity that makes it sag a little bit, but you know that, right? So let's suppose I showed you another liquid. Here's one. We'll see in a second. This liquid surface is right here. There's a cylinder. Okay? And I'm dropping something in that liquid right now. It's a steel ball, 1-inch steel ball. The cylinder is about this big in diameter. Okay, so here we go. There's the steel ball coming down. Bam! Splash like in a liquid, of course. Look at this thing. Well, of course, that's what liquids do, right? There's waves, maybe ripples, which we didn't see. There's splashes. And then there are jets that come up. And then the jets break up even into little droplets, correct? Now, this is not really the crown that you have on the conference proceedings, right? You have those pictures, quite kind of closer. Breaks up, look at these little droplets. But you also see some dust there. What's going on? This is not a liquid. This is 100, or maybe this is 50 micron diameter glass piece. This is not all a liquid. And you know what? Look at this. It's not cohesive, right? You'd say. I mean, this is freely flowing. This is sand. Very loose sand. It's not your backyard. I mean, you can't walk on this. Look at some other thing. See this mark here? See how the whole thing rises? It's as if you stuck your hand in a bathtub and all the sand rises up. It's a very interesting state of granular materials. Very liquid. Would you agree? So, we started that after I saw some beautiful, beautiful movies by Amy Shannon and Sidney Florence, and they were then at UIUC. And I said, we gotta have that. We have to do that too. So we started a program on that, and our David Moses group did some fabulous research on it. So you got even prettier pictures from 20, right? Just check out their stuff. But what is so amazing here is that energy comes in, right? It dissipates and gets refocused. And look at this, it's like a pencil-thin jet. It is totally collimated and even breaks out a little bit. Why is the energy in the cohesion of this material refocusing itself so beautifully? And what is going on? These are collisions of grains, right? I mean, it's billiards. How does it look like? So it's like an ultra-cold fluid. And then really, really, really cold. It all moves together. There's very little velocity fluctuations, as you can see. So here's some questions. What keeps the jet so cold? Right? You take a bunch of glass beads together, and now there's this emerging state, a collective state that has this behavior. Where does all that come from? Isn't that kind of both crazy and amazing? And it's only short-range forces, presumably. How is it different from liquids? And what can we learn from it? So that's how we get through that today. And the other thing to remember is there are no obvious attractions. So if anything, there's no obvious surface tension. By the way, in liquids, the one thing that you cannot vary is surface tension. Right? Did you know that? I mean, honey is different from alcohol, of course. And the density of all liquids is more or less the same, or magnitude maybe. The surface tensions of all liquids are within a factor of 10. You can even take liquid metal, and the surface tension is maybe 10 times that, maybe 8 to 10 times that of water. And water is already on the high end. So all the different behavior we know from liquid comes from viscosity. I mean, you know, you should hit me over the head. That's not quite right, but I mean, you just look at where does that come from? You can't do much with surface tension. All right, so this is the one that we want to look at. So the stills from this. And the first thing we did is actually put it a little bit under vacuum. All right? So here's the same thing under vacuum. This is atmospheric, half an atmosphere and 50th of an atmosphere. And look at what happens. Actually, huge difference. So here you see already that this liquid-like state that you see here doesn't quite occur here. In fact, the jet, as far as the jet is concerned, is much tinier, puny. On the other hand, the spray is much bigger. It hits the wall. See that here? Bam, it's just the wall. That goes out beautifully. Less drag on that. And then this almost looks, there's some intermediate stage, with a two-stage jet. And so I won't have time to tell you all the details, but you can ask me questions about it. I'll just want to give you a flavor. What happens really is that there are two effects we think that work together here. And one is that this sphere that you can see drills a hole, and that hole under gravity falls in. And in falling in, it comes from all sides, and the momentum has to go somewhere. And it goes up, and you'll see in a minute it goes also down. And it gives rise to this little jet. But here, when you have actually air in there between the grains, you get an additional cavitation inside, and that will throw, that has enough energy to move a whole plug of material up and give rise to this huge jet. So let me show you how we got to that. You can't see that from just looking at the top, you have to look inside. This is one of the interesting problems with granular materials, that you can't really look through it. You can't just shine a laser. So what do? Well, here's a tiny little experiment of the jet, X-rays, and we blasted it. Went to the advanced photon source and took out all the stops. A room like this would be brightly lit when the X-rays come out, right? And we need it brightly lit because we go at a meter per second or more. And we're looking at things that we film with maybe 5 or 10,000 frames a second. See a lot of light. On the other side is a scintillator. So here's a close-up view, and the camera has a field of view that's a few centimeters by a centimeter. So that's somewhere in here. And right now, you see nothing, right? You're looking through the material, it's just dark. And now the sphere comes through, and this drills a hole, and the hole fills in slowly. See that here? And the jet is coming out like this, right? Now you take about 17 to 20 of these snippets together, each individual experiments, but they're all actually quite nicely synchronized. If you put them together and you see what really happens here, there's this hole being drilled, it's colliding right here, two jets, see one coming down, and this is a little hard to see, but there's another jet coming up, and then the thing hits the bottom, and you trap air inside here, and now this thing fills up, this air bubble rises, and then will give rise to that big jet at the top, okay? So this material is actually a really interesting material right now. It's almost like a liquid, but it was sand. Now we take images like this, and we go a little bit more quantitatively, so we use a little processing, calibrating our density very, very carefully. So this is now, the colors are the packing fraction, and this is plus 0.06%, and this is minus 0.06% of the green, which is the initial packing fraction. And you see when this thing comes down, drills this hole, the packing fraction is increasing a little bit in front of it, but not much at all. The material is essentially moving out of the way, almost like an incompressible fluid. Now you do the same thing, and you take the air out, and you see now what happens is, so 3 tours, you get a shock, a compaction front. It's like taking a snow shovel and just shoving it against a snow wall of snow, right? You just build that up in front of you. And so what happens really is that during the time of the experiment, the gas has to move fast if it wants to move. And so I give you some times here. So it takes about 60 milliseconds for the time to go through the bed. The bed rises within about half of that. And if you ask yourself, what is the time for gas to diffuse around in the bed? Now remember, it has to go through these interstices between the grains. These are tiny little holes. We estimate that from the permeability, which depends on the grain diameter squared, and then on the packing fraction. What all packing fractions are roughly a half, maybe a little bit more. So these look dangerous, these exponents, but they don't matter all that much. And then the diffusion constant, we heard about earlier, diffusion constant, so it's just the permeability and the viscosity of the gas, tiny, and then the pressure is particular. So it's actually, this situation depends on the pressure. Put in these numbers, and you find that the typical diffusion times are much longer than any of the times in the dynamics of the experiment, right? So the gas just can't go anywhere. And so grains hit a little bit of gas, which hit another grain, which hits gas, like a little spring in between. So this behaves like bathtub filled with water that you jump into.
Explain why the diffusion constant is proportional to pressure.
Yeah, it's interesting, right? So if you wrote a diffusion equation for this particular system, that would come out in this particular case, yeah.
Does the compressibility of the gas have anything?
No, so not in this particular gas. Now that depends a little bit on the speeds, right? So if you're going fast enough, then go.
Because with the reduced pressure, I think you could just, you don't need to accommodate the gas. You just
Right. And so that essentially it works in the same way. So either you say the compressibility is such that it doesn't matter that you have the gas, or you just don't have any gas in the first place. And in that case, it's just grain on grain, and then you compact. And so now, this is just a question. 2 questions, essentially. But what happens for the dense bed? So this was a really, really loose bed, right? And so the one question is what happens for a dense bed that has gas in it, and what happens for a dense bed that has no gas in it. So we just said for a loose bed, let's just recapitulate. All comes in, the material moves away from it, and it can do that because grains basically hit gas and hit grains. The gas can't get away. And basically what I'm proposing here is that having the gas in there prevents local packing density changes, right? Because if the grains were too compact, the gas had to be squeezed out. It can't do that. Diffusion is too slow. If it would want to dilate, other gas had to flow in. But it can't do that. There's not enough time given these tiny little interstices. So what is the outcome of that now for a dense bed? And the interesting thing is this. In a dense bed, an atmospheric, so dense means 0.6%, well, of course, get stuck earlier. Go to your garden, you drop that sphere right there. That's it. But look where it got stuck here. And now, look what happens when you put it in a dense bed, same density, but you evacuate it. Those two, right? So it's exactly opposite as the case that she had with the loose bed. And it is it's a signature of this effect, namely that when there is gas in it, the material doesn't want to change its package. So here was gas in it, it was densely packed, it doesn't want to get loosely packed, it doesn't want to dilate. Remember, blue is dilation, it doesn't really want to open up, because then gas would have to rush into all these new voids, it can't do that. But in this particular case, there was no gas. So, all right, it can dilate, so the thing can go into it. And specifically, then you asked about it, cross over someplace, and you can do these depth time plots. You see this the shock front right here, and you see here the dilation front here, so compaction shock here, dilation here. This is all, by the way, for the case that there is no gas in it right now. And this is the loose bed, this is the dense bed, and somewhere in the middle here, there's a situation where the sphere comes to a stop, and there's very little change at all in it, and that is a critical packing fraction. If you plot this change in packing fraction as a function of the initial packing fraction, you see that that happens at about 58%. So that really is the point at which the material decides whether it wants to dilate or compact. This, again, is an example of really interesting behavior, true fluid behavior now, in a granular system. Okay, and it depends now also, as is, if you want, just one sec, memory of its initial conditions, in the sense that it mattered what packing fraction you started with. So there were two questions right here. One there, maybe, and then one. Go ahead.
Is there any, is it a coincidence that this critical volume fraction at which you get this transition coincides with random loose packing?
Okay, so probably not. But the details of exactly where it is are a little bit murky right now. So look, for those of you who know that, this is a loaded value. I mean, if you went into a conference and said 58%, right? All hell breaks loose, especially if you're in a glass community. Man, oh man, oh man, you know, whether that's now mode coupling or this or that, the other thing, 58% colloids. If I said the wrong word, now I can't get out of here alive, right? But I'm an experimentalist, so there's error bars, so I'd say that's what happens. It is dangerously close to random loose packing, but random loose packing is also notoriously ill-defined, right? It depends on all sorts of things, for example, whether you do that packing or not, right? So, essentially it is at the point, and first you'll hear more when we do the suspensions, it is exactly that point where granularity matters. So if you loosen in that, you maybe have, now in a colloidal suspension system, you can have hydrodynamic interactions and all that. Once you're 50, the spheres, once you're 58 or more, I'm claiming that granularity, right? And here what that means is that, for example, in this particular case, you have this transition between dilation and compaction.
Since packing is so critically important, I assume that you went from spheres to rod-like things, then will be totally different.
Yes, and I bet you're right. And the thing is that nobody has actually done anything like that for non-spherical shapes. I take it back a little bit because, in fact, to get higher contrast for our X-ray experiments, we needed to use beryllium-type particles, and so they were not totally spherical. So I don't think that qualitatively this behavior will change, but the points at which that crosses, for example, this line will certainly depend on this. All right. Let's go back. Yep.
Since your air is behaving as an incompressible fluid, would it be reasonable to say that this is sort of essentially a suspension particle?
Well, so exactly. So the thing behaves more
So
incompressible,
right, maybe there's at some speed it starts to behave like a suspension particle.
Yeah. And so that's kind of the theme. So right now, this suspension as its solvent. First, I'll tell you what happens when you put some liquid. But let's go back to the pictures I showed you before. These are stills from this jet. So now we're not interested right anymore what happened to the jet, but we're just looking at this jet itself. You can zoom in and you see there's some structure, and a little bit later this seems to break up. But these images are actually pretty low resolution. It's the first images we took. It's high speed. It's, I don't know, 10,000 frames a second. But you know, these jets, they can be this big. So you have to kind of step back, and then you lose resolution. So it's this problem that Jerry also talked about earlier. So you have to, on one hand, resolution, time, but also the speed limit. And this is what would happen in liquid, right? It breaks up too. Now in the liquid, of course, you can do something else. If you just want to study breakup, you flip the whole thing over, right? So next, no. So here's work from Sid, and this is just an ordinary faucet. So you see it breaks up here. This is a Rayleigh plateau instability. And the nice thing for water and air is that it has a very characteristic way of breaking up if you look with high speed. See that? And there's another breakup coming in a minute right there, and you get these oscillations of that satellite trunk. In particular, if you look at this, it's a symmetric shape that turns asymmetric. See how it is a cone hitting a sphere, essentially. It's characteristic of ordinary liquid like water and air. So we don't even have the resolution to get anywhere close to this, but we're going to try. Okay, so what do people do in this business? They look at the shape of the structures that form during breakup, and also at the width of the neck as it comes to the singularity where it snaps apart. All right, so Matthias Möbius a few years ago said, okay, so let's take a cup and don't fill it with water and drill a hole in, just fill it with grains and drill a hole in. And the grains come out. And these they come out, and they come out as a funnel. And eventually they form the same structures you just saw in that jet, except this is now a steady state experiment. And you zoom in a little bit, and you see, that maybe looks like it. But it happens maybe 50 centimeters under the open. And now you have this resolution issue, right? You need to go fast, so lighting is an issue. You need to see the whole evolution. You don't know where exactly something breaks up, not like water. So you have to go close, but then you maybe miss it. So this is where John Royer came in and said, all right, here's the solution. We go in a co-moving frame. This is 80,000 bucks, or something like that. And they didn't tell me about what they meant by co-moving frame until they did the experiment, and they came back with some images I'll show you in a minute that were just blowing my socks off. But the idea, of course, is to drop the camera and then somehow catch it. So the John Levy system now, this is about 2.5 meters tall. The sand is inside a container called a hopper. There's an opening here, a nozzle, and it falls down. The whole thing can be evacuated, so we can maybe even get rid of air drag. And there are all sorts of materials we used in there, but typically it's this fine-grained sand-like material. And then we drop the camera, all right? Now here is a version that Scott now built. This is much more improved. The actual system is right here. This is the hopper. The camera is on a sled. These are very low friction rails here. There's our system that catches the camera right there. The camera, by the way, is rated to, I don't know, 100 Gs. It's a crash test, no big deal, but it's the optics that are important, right? And the whole thing can be turbo pumped here. So we're the only crazy people right now that I know of who turbo pump a Granular system. Turbo pumps don't last long, but it's important to make sure that you check that parameter regime. And here is the real time. So Allison was a REU research for undergraduate student with us, and that's what it is. You get 0.2 seconds. Bam, done. I slowed it down a bit. Let's run that again. Pushes a button. There's a magnet that releases the camera. That's it. Now, in 0.2 seconds, you get a few gigabytes of data if you do it right. And this is what you see. Okay, so here we go. We're zooming, and this is the nozzle. This is maybe a centimeter. This is a few millimeters across the individual grains, and this is an early movie you don't see, but you see the stream. Everything is at rest right now that we started. And the camera is accelerating, and it's catching up with the stream. Right about now, see, you kind of see the same notch right there. It's not moving free fall. And look how this breaks apart. Isn't that absolutely stunning? I mean, it's the sand, ladies and gentlemen. It's not water or anything, you know? And it falls apart in this filigree way, and now the camera slammed itself down. All right, let's see that again. There's a couple of things that are really interesting. You see, as this thing keeps speeding up, eventually there is Stokes drag. And even at low pressure, viscosity doesn't change much, there's still enough drag to rip apart particles, which happens about now. See that little stuff is coming up like from a comet. We know the speed at that point. So we know actually the Stokes drag. And so we know what the forces are. And guess what? They are nanonewtons. Whatever holds the stuff together is nanonewtons. Okay? Really interesting. So now, if you put the whole thing in air, well, the whole thing happens always. And it gets all fuzzy. But air is not, for example, leading to streaming that stabilizes or rather initiates the droplet formation. It just smears out the whole thing. So that's not what it is. It's not electrostatics, at least for the system here. We're doing actually electrostatics right now. We have gotten this thing to be now piconewtons in force resolution. And so we can look at electrostatic forces actually. Cool, but for this thing, it's not electrostatics, and even if you replace the grains by, let's see, silver-coated particles, still see that cluster. So, what is it? And, well, in the granular community, the thing that everybody talked about is the same that thing that happens on the freeway, traffic accidents, whatever, inelasticity. And you lose energy, and that gives rise to clustering, of course. Right, so this is the idea. Except now we put in a material that has a higher coefficient of restitution, so it has more energy loss. Roughly same size, same size rather. And look at what happens for copper. If anything, it should cluster more. It's more dissipative, but it clusters less. Even though the coefficient is lower. And this would have been the idea. This is early computer simulation. There are more complex ones now, where you ask yourself, what about structure formation in the universe? Or for these protoplanetesimals, a whole bunch of gas coming together, colliding. And in contrast to molecules, of course, energy is lost in collisions. So these are cold regions where things aggregate, and other things come in and get captured by cold regions, so you build up structures. All right? But here, that's not that simple. And so one has to go back and look at what are the mechanisms for agglomerations. This is now older work, engineering literature, and you look at what that could be. Well, as Singer, of course, well, we don't have that. There's capillary bridges. Well, presumably we don't have a lot of wetness in there, although we cannot rule out molecular layers of moisture. And there's electrostatics, and then there's nanotubes. Now, these two things, they have the same functional form, turns out. And the force between two spheres is proportional to the size, the diameter of the sphere, with the prefactor, which for capillary bridges is, let's say, roughly this, and for van der Waals it is another constant, and it depends on details, but the form is the same. And in everything I tell you, please keep in mind we cannot rule out molecular layers of anything else. Presumably they're really on there. But it's not a lot of difference, because we can bake this stuff. So in either case, it looks like a van der Waals-like type of force. And so what are the magnitudes of these forces? So this is the diameter of the typical sphere. So this is the example for which these curves are calculated. It's not a flat plate with a sphere, but similar for a sphere against sphere. And you see that we are right around here, 100 microns. And so van der Waals is this line, and depending on what you put in, of course, then the capillary interactions are also right here. So these are the forces you've got to worry about. Yes?
Sorry if you already mentioned this, but could frictional interactions play a role? You
What
mentioned
interactions?
frictional interactions, so the surface roughness of the particles.
Yeah, so at collisions.
Yeah.
Yeah, that's a great idea. And it leads me to exactly the next slide. Thank you. So, if we take it from here, that it's these types of forces, then they are very short range forces. I should have said this is the functional form, but they're van der Waals are short range, right? So then surfaces matter. So we're talking 100 micron particles, but van der Waals is nanometers. So we've got to worry about nanometers. So what if we modify the surfaces, right? And that's what John did. So this is a glass sphere that's pretty clean, and there are these things, they're flow aids, in this case called aerosol, you can buy it. It's nanometer sized powder, 40 nanometer diameter, and you sprinkle it on foodstuffs, so it comes out the side of it. That should give it away, right? It flows better. It clumps less. So he puts the stuff on there. And we know the size of these little particles. You can measure it, in fact, with AFM, and now you see that clustering is reduced. Okay? So van der Waals or whatever it is can't catch as much. Now you can do quantitatively, you do AFM measurements by putting two glass cubes on the edge of an AFM cantilever and put it down in another sphere and then pull it back up. But these are, of course, static measurements, right? And this system does it in a dynamic situation where everything is colliding. So this is just giving you an idea what central collisions happen. And you see that if you now put the material on this aerosol, then the distribution comes down here. So less cohesive force, right? So therefore less clustering. Now if you can do it the other way around, also you can take something and put sticky goo on the surface, of course, and it starts to cluster. So here we put about 10 nanometers worth of oil on the surface of the copper, and of course it starts clustering, and not surprisingly, distribution also widens. Yep.
Why does the coefficient of restitution come into play for the copper?
Where does it come from?
Why does it come into play?
Because the idea in the simplest models for collisions of macroscopic bodies is that you combine the place of freedom into one coefficient, which you call the coefficient of energy loss coefficient.
So then I would have anticipated that that would cluster earlier.
Yes, that's what I said. And exactly right, and it didn't do that. And so now, okay, so it is not an elasticity, but rather, that's what we're leading up to. This is really good stuff. It is not simply an elasticity that gets this system together. In fact, elasticity cannot do it by itself, but rather it is attractive interaction.
So are those absent from the copper then?
There are the attractive interactions.
Yeah, are they absent from the copper?
No, but there's one other thing that can come in. So great, you guys are right on target. So there's a balance, of course, right? If I have massive bodies that slam into each other, there's so much kinetic energy that even a little bit of attractive interaction may not be enough to capture. That also comes out of the astrophysics world, and everybody thinks about it. And here's the idea: comes together, bam, something happens, and if you have too much energy, you come back up. There's some sort of a capture potential, right? That we capture velocity. And if you're less than a capture velocity, which depends, of course, on your cohesive force here, you stick. And you notice it depends on the mass, right? And the mass, because of the density of copper, is so much larger, so we lucked out. It's almost actually lucky that between copper and glass, we were just on the two sides, right? So now copper comes out of here. Right? Now, you can do something else. You look at molecular liquids. Sorry, this is stuff. So for molecular liquid, this is a potential and as a function of distance. So it's actually water, 2 Leonard Jones type things. Drawn here, or empirical Leonard Jones. Potential is that this is a minimum. All right? That's how you define surface tension. You say, where is that minimum located? What's its magnitude? That's for molecular liquid. That's one way to get at the surface tension. And it's very simple. You just say the surface tension is the depth of that potential divided by that distance squared, the molecular distance. And one way, of course, to get to very low surface tension, effective surface tension, is to change this potential. But that doesn't really happen in molecular systems. And here, we already said it's the same van der Waals force that happens between molecules happens here too. So that's it. But it's sigma, this distance. And now we're talking macroscopic bodies, it comes in square. So you get to the effective surface tension in this system that you just plug that in. That is here, 0.1 micronewton per meter. Now what's water? 70 millinewton per meter. So anything that you can take off the shelf here, it's at the triple point, would be of the order of 10 to maybe, 70 millinewton per meter, or 70 millijoule per square meter, right? Milli. This is 0.1 micro. So we're 10 to the 4, 10 to the 5 lower than the ordinary liquid. So if you think of this as a liquid, it is actually a remarkable liquid regime. It is one that you cannot get to with ordinary liquids. Yes?
For D there, are you using the diameter?
Yeah, I'm using the diameter. Yep. So This is a regime that you can get to with colloids also. So Alphonse van Bladeren has been in this group, I think, was it I don't know, in Holland, they did that with colloids. And they also can get to, because of this number here being large, to some very, very low interfacial tensions in this case, right? But it's really not surprising that the shapes are different, as we see also the behavior will be different. And of course, it's not clumping together. There's not enough energy to minimize any surface shapes, right? There's no KT that allows these molecules to move around. You're kind of stuck in where you're at. So what is the idea? We're going to do now some simulations to get at more microscopic details. And this is just a way to hint that we can calibrate our 3D MD simulation pretty good. It's about 100,000 particles in a hopper. Calibrated in a hopper, actually, and this is the stuff that comes out. This is the experiment, this is the simulation. You put in reasonable parameters to try to match the flow rates and all that, and the coefficients as far as we know. What happens is that there's a lot of interaction of the grains right here. So there's shear, things are hot, and now gravity is pulling on this system, right? And if you drop two stones behind each other, you know that they will separate over time. Eventually, they won't even see each other anymore, and so that means that system will get cold just by gravitational stretching. That's actually interesting. Our system allows us to, with this extra parameter of gravitational stretching, just give it away something, to separate out elasticity from cohesion. Because if something just came together because of an elastic collision, but no attractions, right? Then this gravitational pull can slowly pull it apart. Right? But on a freeway, on a surface, that's going to just be stuck. So things cool, right? And so here are some ways of how we do that. We just use a very, very simple well for this. So on the way out, the particles experience a little force, not on the way in. On the way in, there's no force except when they hit. There's the usual interaction of hitting. They form a little bit the particles, and then they come back out, and then they, on the way out, they experience as well. That's mimicking sticking, or due to either van der Waals or maybe capillary interactions. And then once they get out of this well, they are in a really short range. And we set this to about 1,000th of the grain diameter, which corresponds roughly to what we measure experimentally, maybe about the order of 10 nanometers or so. So what do you get? So here are two examples for different. So these are actually rather big grains, 2 microns. The orifice is 3 millimeter, and gravity is running left to right. And the grains are colored such that if there's a lot of relative interaction, velocity, it's hot, it's red. And then the pink guys are grains without any neighbors, so they're just irrelevant, they're sprayed, they come off, right? And you see that slowly this thing is cooling. It's actually collimating. That's due to elasticity a little bit. Some of the guys, of course, get kicked out, right? But then eventually, as you see here, it is just slowly drifting apart. The whole thing is just falling apart. And that's what this gravitational stretching does. Now contrast that with a situation where we put the cohesive force larger. And what you see here is more collimation, okay? And you see fewer particles coming off, and you see these shear bands. See that? You concentrate this in the region. It's almost like it's being stretched apart. And now watch what happens when they become loose. Bam, they cool. They freeze. They're stuck. All right? So this is exceedingly rapid cooling of this liquid. All right, and then this swings around, hits this point. You see impact right there, and then it opens down.
So this is simulation?
This is simulation. Because we can't do this, or we can't measure in our system within each grain the relative velocities. We can't look through. We don't have X-rays at 10,000 frames a second. So now in this game, what people do, they say, well, there's no real temperature, but there's a granular temperature, which is just the RMS velocity fluctuations, deviation from the mean, and you should track that. And if you do that, actually, so Z is the distance downstream. Here's where it comes out of at 0, out of the nozzle, And you see as the material is coming towards the nozzle, so this is the hopper, let's say there's an opening right here, the stream of particles comes down here, right? It has a lot of shear right at this point, so the temperature goes up if you define it that way. And then it's entering free fall and it's coming up. But you see, there's not much difference between the different curves here and there for various different elasticities. So it's hard to tell any difference. So we put this data on a log scale, let's say. Okay, fine. Now you see something, but it's not even dramatic. Except you see this bump right here. By the way, you can do that both for the radial velocity. So radial, and we can also do it for the z velocity. So this is an anisotropic temperature potential. And so if you do it, for example, the z velocity, you see this bump again, and then if you ignore the green and the blue curves with the bump, and you just look at the other ones, they follow this -1 law. Now, this bump corresponds to the case where you have grains forming, droplets forming. It actually heats up first as the shear, and then it rapidly cools. Yeah? And everything else just is freely expanding. It's like adiabatic expansion, and it follows this particular law right here. It gives you this -1. So it's just like you would do in a cryogenic gas expansion, where you have gas come out of the nozzle, just cools. So we have to look at something else, and that something else we cannot do on the experiment. We have to do on the computer, and that is we have to look at locally how are particles connected. So it's not so much the temperature, I think, that gives it away, but the connectivity between particles. And if you start from the nozzle, which is right here, and now you say to each of the particles, how many neighbors do you have? And how does that change as you go downhill, downstream, as you fall down? Then you see a real trend that some of these particles get more neighbors and others get fewer neighbors. And everything is normalized by the number of neighbors they had at the beginning. So in some cases, there are these clusters that come out preformed, right here. And we track them over distance, and we say, are you losing or are you gaining particles? Right? And the interesting thing that you see here is when the cohesive force is 0, which we can do, it always loses particles, so this stuff is drifting apart. And you need to have some cohesive force, now details depend, right? And in fact, you can look at a phase diagram of changing things. So anything from a spray, which eventually just turns into individual unconnected particles, to something that is so cohesive it doesn't even come out of the nozzle. And then liquid like big droplets in between. So droplets are things that contain maybe hundreds of particles. Clusters are things that contain maybe 2, 3 dimers, primers, that sort of thing. The chemist would be interested in what happens to that. And at 0 cohesive force, it doesn't matter what your elasticity is because you're always drifted apart. And so the cool thing from that is that you can use it as a diagnostic of grain-grain interactions, now that we know all that. So imagine the following. You start with some material that you don't know the cohesive cohesion of the particles. You have in your hopper and let it fall out. And now you position yourself far below the nozzle. And you just take snapshots of the grains. And imagine you could count how many particles are in those grains on average. And then you measure numbers. Each color corresponds to a certain average number of grains. And we know because we started off with them, right? And they either gained some or they lost some, but they ended up with this number. And there's a one-to-one correspondence between where they ended up and where they started off, except maybe up here. And that means that if you look just at the bottom, which is this plot right here, there's this curve that connects the cohesive force with the number of grains that you have. So actually you can use it as a diagnostic for measuring grain-grain interactions. Again, this is the same as you do with molecular beam apparatuses. So this is the macroscopic equivalent of a molecular beam apparatus, where you have molecules come out of the nozzle. There's a short time where the density is high enough to interact. They form dimers, trimers, whatever, and they drift apart, and you have your spectroscopic measurement at the end, and you look at what did I have. And that's exactly what happens here. So for example, here they come out of the nozzle, the density is high enough, the cohesion is high enough, these colors, increasing cohesion, they capture neighbors during local collisions, and then they just keep drifting. Right? And these guys, they come out and they hang off the nozzle, and they break up, actually, into smaller clusters. And look at the numbers here. This, for example, right here, can capture some, but it starts out with maybe less than 10, and it comes to about 10 grains. And these here, they have hundreds, maybe close to 1,000 grains in them. The whole range between dimers, trimers, to real big droplets. Okay, a couple more things and then I'll close. So this is just a picture of what one of these things looks like when it comes out. But our computers aren't good enough right now. We just can't do anything about the breakup dynamics here. So I would like to know how do these nicks actually change over time? Right, but it takes too long to run these simulations right now. The biggest computers we have access to do that right. So let's show you. I'll show you what I have, and we'll see how it goes. So here's experiments, and this is the best about computer simulations right now. The simplest thing to start with. Let's just say how big are the clusters? But when they broke up, they don't change anymore, right? This is not a liquid where surface tension makes it into a sphere. It's frozen. So it's easy to measure the aspect ratio. And interestingly enough, for all sorts of experiments, all sorts of cohesive interactions, anything you can think of, all this jumble of data falls between two lines. Now, you liquid guys, you need to jump up now and say, wait, plateau, I know what happens. The wavelength for this instability, where it is driven by surface tension, right? A cylinder of liquid is unstable if left to its own devices, and surface tension will strangle it. There's an unstable wavelength that is characteristic of that, and the aspect ratio that comes out of that is pi. So the smallest drops for liquid, the aspect ratio would be pi. This is small, so it's not, of course, but it's crazy. It's different from an ordinary. Now, the simulations seem to do an okay job. I mean, actually, from this cluster of data points, you can't really see it. If you look at the histogram, it's around 2. That's okay. Our simulations probably have plenty points here because our screens are not wide enough in diameter. It's hard for us to get enough particles across the width. And so that's one thing. The other thing is we're not able to run these simulations long enough, so some clusters would break up lower, but we just ran out of time. So maybe that's why there's this little bump right here. So I don't know yet, but it's possible that this would actually fill it. What sets that wavelength? We don't know. Nobody knows. It's a great research question. So what about the dynamics themselves? So how does the width of the neck depend on time left before the neck snaps? Now I told you that in a viscous liquid, really plateau, it's viscosity that does everything. Closer to the breakup, gravity doesn't matter anymore. Things go so fast, surface tension is so strong, it's strangling the pore drop just like that. In our case, surface tension is so low that you might say, well, if there's any strangling, fine, but there's also stretching, right? The thing has more time to be yanked. And we don't really know what the ratio of the two things is right now. One thing that you can see is from snapshots, these are milliseconds before breakup, so it happens somewhere between here. You see that the shapes of the droplets are clearly different from 6 droplets, right? They're on average more cone-shaped. You see that? So that's not like water. But guess what? I mean, this is really mind-boggling, and it would be wonderful if somebody came up with a good explanation. If you measure the width as a function of time to break up, and you put all the data on there, and of course the data isn't good enough to claim anything with certainty, but it is suggested that the power is not 1, like a viscous liquid, but rather it is very close to 2/3, which is what that line is. And 2/3 happens to be the exponent for the inviscid case. So even though it doesn't look like water, it is not water, it behaves like water. Now in water, you have this behavior, right? 2/3 inviscid. And you know what the prefactor is. It's inviscid. Viscosity is out of the equation. So it's density and surface tension. So this is another way to get at this effective surface tension. Now you plot, and you know what the intercept is, and you pull that out from the data, and you find out that for reasonable estimates, you know, packing fraction, all that again, it is micronewtons per meter. So that is actually, so but why should this even work? Well, it turns out that this is, if you know that viscosity doesn't matter, right, it's dimensional analysis that will give you this relation. So it might have nothing to do with inviscid or anything, it's just that with water, I should say. But rather that if you know that it's only potentially surface tension, potentially density, and time, that's the combination. But where does it come from, we don't know. Okay, 2 more slides. So here's what we see. But this is what you also find. This should be interesting to some of you. This is a simulation out of a nanojet. All right, so now you see these particles? These are now pentane molecules with all the chemistry, everything in there. That's Uzi Lampman. He throw it all in there, a whole interaction potential. And he pressurizes this pentane, I think it was a hexane, out of a nanonozzle, right? Enormous pressure. Tiny, look at that, picoseconds, or nanoseconds, 1.3 nanoseconds. And it doesn't look so unlike what we see, right? It looks exactly granular, I would say. Now, it turns out that this is explained right now, not as really plateau, because it doesn't follow really plateau scaling, but rather as a thermally driven instability. The idea is that for an ordinary liquid, you don't look at these tiny scales. So it's all really plateau. If you have this situation here, nanojet, then really plateau is preempted by thermally driven instability. That you can look up here against FSK. Maybe, with some crazy exponent. But in our case, it's not thermal, it's not really plateau, and still it's 2/3. And so keep your 2/3 in mind, because, well, I'll show you that for suspensions on Thursday, and it is really amazing how the 2/3 always comes out. So with that, I'll let you read this, but I also take your question, I'll try. Thanks.
So what is exactly the nanojet?
The nanojet is a simulation of pentane molecules that are pushed out of a nano-sized nozzle. Right? So, and in our case, I would say that there are, at least on the face of it, striking similarities in terms of the shape now, but not of the scale. So there's something that doesn't jive, right? Water has a different shape, but the same scale. The nanojet has different scaling, but has similar shape, right? So we don't understand this, and I think it's a really interesting problem to get. Anyway, thank you. So I think you were first.
So I'm really surprised that this actually behaves like really flat Earth. And I was actually thinking maybe you could come up with these, your granular, whatever, treat them like molecules and look at them as tiny different molecules, but the distance between these molecules is different, like it's not the distance between liquids. So you have bigger molecules with bigger distances, but they behave like liquid, and then you come up with a viscosity, with an effective viscosity or collective viscosity and density, and then you can treat them as liquid.
Yeah, that's a great idea, and in some sense, that was our idea for the simulations, right? So to say, well, we treat that as, Uzi would treat his thing, except he has a complex interaction potential in there. It's not contact.
But I can't come up with something with surface tension. I don't think that's very surprising, because here you really don't have the surface tension, but you see a similar effect.
No, but look, what I'm saying is there's an effect that mimics or that masquerades like surface tension. So what is really surface tension? It's a tendency of molecules to hang together, and our particles hang together. And this whole surface minimization, you only get if the molecules also are at room temperature, if they can move around, and all that extra stuff. But I'm just taking the core, interaction part that gives rise to surface tension or surface energy. So you could do that for a solid too. And that would be this attractive interaction. I just say it's short range, and I put it in the simulation. And then I get numbers out that seem reasonable, but what I hope, of course, is that you all go like, I don't know, this is fishy, and you go home and you calculate it and you come up with a really great idea of how this actually hangs together.
So with the granular clustering, you showed that there was a delayed onset of clustering when you reduced the pressure, right?
Over the jets.
For the clustering of the column. Is that right?
So when I reduce the pressure, then, okay, so this is really separate. The clustering, I would say, is always driven by this type of interaction, right? So elasticity alone can't do it. Whether the jet is really big or the jet is really small has not to do with this, but has to do with whether or not there is interstitial air in the system. That's what I was.
But I mean, the formation of the granular drops, so that happens later in the game when you have lower air pressure.
No, that happens just later in the game after the air pressure has nothing to do with that. What I would claim is that the air pressure itself does not directly affect the onset of this clustering or anything. What it will do is it will, and if you let them fall through air, it'll rip them apart over. That's all. If you got rid of the air, then you still see the clustering.
At the same point, the distance from the nozzle.
No, so the distance from the nozzle, I don't know the answer, and all I can say is, okay, so then you're right, in terms of distance from the nozzle, down here, if you have air, right, you start breaking things up early. Okay, so maybe I misunderstood what you said. In terms of distance, right?
Yeah.
Okay. Oh, sorry, Jerry was right.
Just quickly, did you do anything to make sure your materials were clean? In these this small attraction, are you sure that this is characteristic of the clean material that you were using and not of some adsorbed impurities?
Okay, so no.
Yes, it is. I don't know.
So this is not a surface science experiment. I can do surface science. I've done surface science experiments at 10 to minus 10 torr. This is not 10 to minus 10 torr. So this is 10 to minus 6 torr. And so therefore there's always an absorbed layer of water vapor on all of these. But what I'm saying is that it doesn't matter because as long as there's no liquid bridge, the shape of the force between nanomoles and a layer or two or 5 or 10 water vapor is the same.
So you're saying it is really basically water?
I say I cannot experimentally distinguish, so we have baked it, we have done anything we can do. But you know that at 10 to minus 6 torr, it takes 1 second for one monolayer to absorb on a surface, right? So I mean, we cannot rule that out.
Yeah, I'm really just asking about the microscopic origin of the attraction and how I should
You should think of it, I think of this as a van der Waals-like or a surface layer-like force, and it has this, well, I don't like to use the word capillary because most people I talk to associate with capillary forces things that look like this, right? And that, I know, there is none of that on there because we've done every surface technique that we can think of, and this and the other thing, to check that. I mean, so there's no mesoscale liquid puddles on there, right? But 1 or 2 or 10 layers of H2O, I can't detect.
Thank you.
Have you guys measured the force between these?
Yes, we did. Yeah.
And is the scaling right for van der Waals?
Absolutely. So, great. This is exactly what we did. And so here are these results. So, for example, you can look at this. So the range actually is so short, it's a few nanometers only. So there's a sphere glued on a cantilever, brought down on another sphere, and then put down on the same sphere at other spots, and then take other spheres, put them together to have maybe 100 or more sphere-sphere contacts to get statistics, right? And you get forces that we can't even write out the potential curve. So the cantilever gets sucked down and then it pulls off. So this is just, this dotted line is essentially pulling it off. The potential is so short range that with our AFM, or the typical digital instruments, AFM, you can't resolve the range of the potential. So it's a few nanometers, maybe 10. And then if you go to a sticky layer of 10 nanometer on it, you see the beginning of being able to map out a curve, right? So this is coming in, and this is pulling it off. And here the cantilever snapped back because you went out of the potential. Right? So you can get some sort of estimate. You can integrate that up to get an estimate of what the cohesive energy of that thing will be. And so this is totally in line with either a few layers of some absorbed molecules or animals. And so we, I can't tell the difference between the two.
At the beginning of your talk, you showed the dropout of the water on a leaf, and you said that it's spherical because of surface tension. So if you took loose, dry sand and put it in a ball, it wouldn't remain a ball. And naively, could I think about that as just being due to the fact that because the surface tension is so low, the gravitational length, the gravity basically just spreads it out?
Absolutely.
And if it were sufficiently smaller than the gravitational length, then it would indeed be a ball of sand, like a liquid droplet?
Yeah, so if you levitate it actually, does that
So-
happen?
Yeah, so no, we can't do that, but it's a great idea. So let's suppose I could make with my hands little balls of sand and I throw them out here, right, out of that nozzle. There's a little demon in there. This is now free fall. And let's suppose we got rid of all the air so there's as little drag as possible. They would remain little balls. They remain whatever they are or were at the moment they ripped off, right? So in some sense, it's a beautiful way of looking at a snapshot, frozen in time, of what happened when they ripped off. And it turns out I can't generate them totally spherical, and if I did that on the gravity, right, then of course it will move into the sand.
And what's the size of the
So in this case, all of this works, of course, as long as the particles are small enough so that they can get captured by these forces, right? And since we think these forces are of this liquid layer van der Waals type, it is about 100 to 200 microns depending on the material. Yes?
So if you levitated them in a magnet or something, would you
Yes.
see them? You would see them in spheres, or?
Oh, that would be nice. I don't imagine if you could levitate them, that would be lovely.
Okay, I have one more question. So you showed the graphs with the F versus distance, right? Right before the plots.
The what?
You measured the force versus the distance
Yes.
with the AFM.
Oh, with the AFM, yeah.
Does that show? I'm not sure I understand it. Does that show that relationship there with the surface tension, or is that? So can you prove that relation with the surface tension?
No, not from that plot. So you need. So this is force as a function of size of the particles,
Oh yeah, that's right.
right? And so what I did is force as a function of distance.
Distance, yeah.
Now, also remember, this only works. So if I had a particle this size, right? This force would be so strong, I could never get this lifted off. I mean, yes, this is all responsible for us to be able to walk. I mean, we couldn't live without all of this. But this force does not scale with diameter beyond a scale of a few microns. Because otherwise you could never touch this and get your hand up. I mean, you'd be stuck to anything. It's just not true. And so this is a calculation of ideal spheres, right? Like this, some distance apart, or with a liquid layer apart. And so what in reality happens is that these spheres have asperities, and what people do is they substitute this asperity radius in there. It's all very ad hoc. And so at about a micron or two, you stop putting in the actual distance if you want it to be quantitative, and then probably it is just an asperity size, right? So in other words, up to a few tens of nanometers is all, nanonewtons is all cool, but you cannot get newtons out of this just by scaling up the speed.
And does that, can I ask one more?
I'm here, I don't know about you. Go ahead.
Does that mean that you, does that mean that you can do all sorts of, so if you have these forces between the grains, does that mean that you can go, you can observe all sorts of sort of fluid instabilities with granular?
So that was our hope. So why did we build this experiment? To look at other things beyond this, right? But
Could you repeat the question?
so having this apparatus, could you see fluid instabilities?
Yeah, all sorts of fluid instabilities, because you effectively you're saying that you have attraction between the grains, which is not what people thought initially, I guess. And,
Right.
and therefore,
Yeah, so most people initially thought it was just an elasticity activity. Now we say that, well, elasticity plays a big role. It collimates the steel, prevents things from flying apart. But then it is this cohesion that actually holds it together. And gravity is taken out, also in this jet that comes up, of course. But what else could you do? And so the one thing that we thought of, and that's what Scott is doing right now, is look at electrostatic interactions. So we want to look at longer range interactions. And so since we have this resolution now, we can actually look between individual grains at a giganewton level and see how they interact, right? Due to a few thousand extra electrons in the grains.
it
And
makes
that's-
material.
It's very exciting, and you get clustering and all sorts of things from that also. But that's a slightly different story.